In a shallow tank of seawater, a flounder is doing the one thing its entire lineage has been shaped to do. It's buried. Sand over the back, both eyes flush with the grain, the gills barely moving. Nothing about that patch of bottom says fish. And then a small shark, a dogfish about the length of your forearm, drifts across the tank in a lazy diagonal, passes over the spot, and stops. Not slows. Stops. It turns, drives its snout into the sand, and pulls the flounder out. Finding dinner is the boring half of that story. The interesting half is that the flounder had done everything right. The camouflage was working. The stillness was working. In the version of that experiment run by a biologist named Adrianus Kalmine back in the early 1970s, the hiding place got even better. He covered the buried flatfish with a chamber made of agar, a jelly that lets electricity pass through but seals off every smell and every ripple. The sharks came anyway. They went straight for the chamber and bit at it. Then he took the fish out of the equation entirely. He buried a pair of electrodes in the sand and pushed a current through them so faint you'd need good instruments to notice it. No scent, no movement, no shape. Just a whisper of voltage in the water, shaped roughly like the electrical field that leaks out of a living animal. The sharks attacked the electrodes. Some of them ignored chopped fish sitting a few inches away to do it. So here's what that flounder was actually up against. Every living animal in the sea is, in a small way, an electrical device. Muscle contractions leak current. The membranes in your gills, the ion gradients you have to maintain just to stay alive, the involuntary pulse of a heart, all of it bleeds a faint field into the salt water around you. Salt water conducts beautifully, which means hiding in the ocean has a floor you can't get under. You can stop moving. You can match the color of the sand grain for grain. You cannot stop being alive, and being alive has a signature. The sharks and the rays found that signature and built an organ to read it. They're called ampullae, of Lorenzini, named for the 17th century anatomist who first described them and had no idea what he was looking at. Run your hand along the snout of a shark, and you'll feel small pores, hundreds of them on some species, thousands on others, clustered thickest around the head. Each one is the opening of a tube filled with a clear jelly, and each tube runs back to a bulb of sensory cells. The jelly is an extraordinary conductor. The skin around it is not. So the tube behaves like a very long, very well-insulated wire, comparing the voltage out at the pore with the voltage back at the base. The sensitivity numbers on that system are the kind of thing you read twice. Working with free-swimming sharks in the open sea in the early 1980s, Kalmine reported responses to voltage gradients of about 5 billionths of a volt across a centimeter, 5 nanovolts in the usual shorthand. That's a level so faint that the ocean's own background electrical noise, seawater sliding through the Earth's magnetic field, becomes something the animal has to filter out to hear anything at all. That's the detail that matters. Nobody evolves an instrument that's fine for fun. Precision like that is expensive. It costs tissue, it costs brain, it costs development time. An organ gets that good only when something on the other side of the arms race has gotten very, very good at not being found. That's really the whole story here, and it's worth being clear about it early because once you see it, you can't unsee it. Every weapon down there is an answer to a specific problem, a narrow, particular, identifiable problem, posed by a particular animal that was trying very hard to survive. The shark's electrical sense exists because prey learned to go silent and still. Teeth got their shapes because prey learned to struggle. Venom exists because some predators can't chase. Read any piece of ocean weaponry closely enough, and it tells you, in detail, what it was built to defeat. So we're going to walk through a single hunt, one predation event broken into its stages, because a hunt in the ocean works like 5 separate exams taken in order, where passing one gets you nothing except the right to attempt the next. You have to find the animal. You have to get close to it. You have to land the strike. You have to keep hold of it once it starts fighting. And then, believe it or not, you still have to get it inside you, which is where a shocking number of ocean predators fail after doing everything else perfectly. Detection is where we start because detection is where most hunts die. Back to that buried flounder for a second, because there's a detail in it that changes how you read the whole thing. Carelessness had nothing to do with it. A defense that had worked for a very long time got outflanked by a sense its ancestors never had to plan for. Burial and camouflage are answers to eyes. They're excellent answers to eyes. Against a system that reads bioelectric leakage, the entire strategy is aimed at the wrong sense organ. And you can watch prey trying to close that gap, which is where this gets eerie. Some sharks lay eggs in tough, leathery cases, and the embryo sits in there for months, developing, with a slit in the case to let seawater flow through. That slit is a problem. It's an open door for anything that eats eggs. So researchers in Western Australia, in work led by Ryan Kempster, tested what happens when you present a developing bamboo shark embryo with a weak electric field of the kind a predator would produce. The embryo freezes. It stops beating its tail, stops circulating water through the case, curls up and holds still. It goes as electrically quiet as it can manage, and it stays that way until the threat signal ends. That's an animal that has never seen anything, never eaten anything, never been outside its own eggshell, and it already knows that its own life processes are broadcasting, and that the correct response to a hunter is to turn the volume down, which tells you something about the pressure involved. The counter move to electroreception shows up before hatching, and the predators didn't stand still either. The most obvious piece of evidence for that is swimming around right now with a head shaped like an airplane wing. The hammerhead's head is one of the strangest structures in the ocean, and for decades the standard explanation was that it works like a bigger antenna. Spread your electroreceptive pores across a wide flat blade instead of packing them into a pointed snout, and you sweep a broader strip of seafloor with every swing of your head. The research complicated that a little, in a way I find more interesting than the tidy version. When Stephen K. Jura and Kim Holland tested scalloped hammerheads against sandbar sharks, close relatives with ordinary snouts, the hammerheads were not more sensitive. Pore for pore, they detected roughly the same faint fields as the normal-headed shark. What the hammer buys is coverage, the same sensitivity, dragged across a much wider search path, sampling more square feet of bottom per second of swimming. And there's a second payoff that came out of later work by Michelle McComb and colleagues. The eyes at the tips of that blade give a hammerhead a wide field of binocular overlap in front of its face. Depth perception, right where the mouth is. So the head is doing two jobs at once. A search engine and a targeting system fused into a single weird plate of cartilage. And the reason it's shaped that way is that the animals it hunts are flat, buried, still, and small. You don't need a wide format sensor to find a whale. You need one to find a stingray under 6 inches of sand, which is exactly what hammerheads do. And it's the most vivid demonstration you'll find of what detection means at this stage of the arms race. A great hammerhead hunting a stingray doesn't wander around looking. It cruises, head swinging in a slow sweep like a metal detector at the beach, and when it gets a hit, it pins the ray to the bottom with the flat of its head and works the tip around to the ray's wing. Now consider the stingray's side of that exchange. The ray's whole defensive strategy is burial plus a venomous barb on the tail. Both of those are good answers to most predators. Neither one is an answer to being located while motionless and then pinned by a head that doesn't have to get anywhere near the tail. The sawfish took the same idea and pointed it forward. That long-toothed blade sticking out of its face is loaded with electroreceptors along the underside, and Barbara Weringer's work with freshwater sawfish showed the animals using it exactly the way the anatomy suggests. They detect prey in the water column, Then swipe the rostrum sideways at speed. One tool that finds the fish and then hits it. The saw is a sensor and a club at the same time. But here's the limit that reshapes everything else about ocean hunting. Electroreception is a close quarters sense. A bioelectric field falls off brutally with distance, so even with that ridiculous sensitivity, the useful range is on the order of a foot or two. It covers the last few moments of the hunt. The finding has to happen on other channels entirely, which means the ocean's predators need a layered stack of senses, each one covering a different band of distance, and the arms race is running separately inside every single band. Take smell, the long-range channel. You've heard the line about a shark detecting one drop of blood in a swimming pool, and it's exaggerated in the way most sensory records are exaggerated, but the underlying capability is real. Sharks pick up certain compounds at concentrations down in the parts per billion. The clever part is what they do with a smell once they have it. Water isn't air. An odor plume in a current doesn't spread into a neat cone that you can climb like a staircase. It shreds into patches and filaments, so at any given instant the concentration at your left nostril versus your right nostril tells you almost nothing reliable about which way the source is. Jane Gardner and Jelia Tema tested this on smooth dogfish with a setup that let them control which nostril got the odor and when. And the sharks turned toward whichever nostril was hit first, even when the other nostril got a stronger dose. They're comparing arrival times down to fractions of a second and letting concentration go. That's a fundamentally different algorithm, and it's the right one for a turbulent medium. Concentration lies. Timing doesn't. The praise counter to that channel is exactly what you'd guess, and it's the reason wounded fish behave the way they do. A healthy fish leaks very little. Injury changes the equation completely, which is why a struggling or bleeding animal in open water is on a clock that has nothing to do with how fast it can swim. It's advertising on a channel that reaches for hundreds of yards. Then there's the middle band, and this one gets overlooked constantly, even though it may be the most important sense in the entire ocean. Run your finger along the side of almost any fish, and you'll find a faint line running from the gill cover to the tail. That's the lateral line, and underneath it sits a row of canals filled with fluid, punctuated by tiny hair cell organs called neuromasts. What they read is flow, pressure differences, the push and pull of water moving across the body. What that gives a fish is something we don't really have a word for, because we don't have anything like it. It's a sense of touch that extends outward into the water for roughly 1 to 2 body lengths, mapping every disturbance inside that bubble. A fish in total darkness knows the wall is there. It knows another fish just accelerated behind it. It knows the shape of the current curling off a rock ahead. And it means that in the ocean, movement itself is a broadcast. This is the fact that governs the entire next stage of the hunt, so it's worth being precise about it. When you swim, you don't just go forward, you push water. That water piles up in front of you and rolls off your flanks, and every animal within a couple of body lengths that has a lateral line, or antennae, or sensory hairs feels it arrive. There is no such thing as a silent approach through water. The physics forbids it, which means every ambush predator in the sea is solving the same problem, and the solutions they've come up with are some of the most refined pieces of engineering in the natural world. We'll get to those, because that's the second exam. First, one more piece of the detection problem, and it happens in a place where all of this gets rewritten from scratch. Go down past 650 feet or so, and sunlight is essentially finished. Past 3,300 feet, there is nothing left of it at all. That's not a small habitat. By volume, the dark ocean is the largest living space on this planet, and the majority of animals down there make their own light, which sounds beautiful, and it is. And it's also a catastrophe for anyone trying to hide. Because in a world with no ambient light, you don't hide by being dark. Being dark is easy. Everything is dark. You get found by being a silhouette, or by being the only thing that glows, or by the exact quality of the light you produce. The rules change so thoroughly that the arms raced down there produced weapons that read like science fiction, and one of them is a searchlight nobody else can see. Start with the geometry, because the geometry is what creates the weapons. In the upper part of the deep, in that long twilight band, where a trace of sunlight still filters down, there's a fundamental asymmetry in the water. Above you, the water is very slightly brighter. Below you, it's black. So if you're a predator, there's one direction that's better than every other direction, and it's up. Anything swimming above you is a dark shape against a dim gray ceiling. Anything swimming below you is invisible. Evolution noticed this. That's why so many deep-sea fish have eyes that point straight up, permanently. Tubular eyes built into the skull and aimed at the sky, packed with light-sensitive tissue, staring at the ceiling and waiting for something to cross it. The barrel eye is the showpiece. It's a small fish with a transparent dome for a forehead, and inside that dome sit two green tube-shaped eyes looking upward through its own head. For years, everyone assumed it was locked into staring straight up, which would make eating awkward since the mouth points forward. Then researchers at the Monterey Bay Aquarium Research Institute got good footage of a live one and found the eyes rotate inside the transparent shield. It watches the ceiling, then swings its eyes forward as it rises to feed. That's the hunter. Now put yourself in the position of the animal being watched. You're a small fish or a shrimp swimming 1,000 feet down. There's not much light, but there's enough that your body blocks some of it. From below, you are a hole in the sky. You cannot fix this by being darker. Being darker makes you a better hole. So the ocean invented the strangest camouflage on Earth. You light yourself up. It's called counter-illumination, and it's exactly what it sounds like. Along the belly and undersides, the animal carries rows of light organs called photophores, angled downward, glowing at a brightness tuned to match the faint light coming from above. Get the intensity right, and the silhouette disappears. From below, you red as a patch of ceiling. Hatchetfish do this. Lantern sharks do this. Many deep-sea squid do it. And the engineering involved is much fussier than just switching on a light. The brightness has to change with depth, with time of day, with cloud cover overhead. Some species have light sensors on the top of the body that measure the downwelling light and adjust the belly glow to match. Some have filters and reflectors that shape the color and spread the beam so it doesn't look like a row of dots. In lantern sharks, the photophores sit in the skin in patterns that seem to break up the outline as well as erase it, which is a phenomenal defense. So of course, something evolved to beat it. The weakness in counter-illumination is that the light an animal makes is never quite the light the sun makes. Sunlight filtering through hundreds of feet of seawater has a particular spectrum. Bioluminescence has a different one, usually a narrower band of blue-green. To your eye and mine, in that dimness, they'd both read as a vague blue smudge. But if you had a filter that darkened the true daylight spectrum more than it darkened the animal's glow, the disguise would fail. The camouflaged fish would light up against its background like a phone screen in a dark theater. A number of deep-sea predators have yellow pigment in their eye lenses. Yellow lenses do exactly that job. They cut the shorter wavelengths that dominate downwelling light while letting the bioluminescent band through. And the effect, at least in principle, is to make counter-illuminating prey visible. This is still an inference from optics. Nobody has followed a yellow-lensed predator around and watched it pick out a counter-illuminating fish. And that's worth flagging. The pieces do line up uncomfortably well, though. The animals carrying yellow lenses are predators. They live at the depths where counter-illumination pays off, and the filter does the one job that would break it. And that's just the defensive counter. There's an offensive one, and it's my favorite piece of equipment in the entire ocean. Almost everything in the deep sea sees blue. Blue-green penetrates seawater better than any other color, So eyes down there are tuned to a narrow window around it, and red light effectively does not exist at depth, which is why so many deep-sea animals are red. A red shrimp in blue light is black, it's free camouflage. Now, the dragonfishes of the genus Malacosteus, along with a couple of relatives, carry a light organ under each eye that emits in the far red, out past 700 nanometers. That light is functionally invisible to almost everything down there. Their prey can't see it, their competitors can't see it. And because most of the animals around them are red-bodied, that red beam lights those bodies up beautifully. So the fish is walking around with a searchlight that only it can use. The obvious question is how it sees its own beam, since it's a deep-sea fish with deep-sea eyes. The answer, worked out by Ronald Douglas, Julian Partridge, and their colleagues in the late 1990s, is worth hearing twice. Inside the retina of Malacosteus, there's a pigment that looks like a derivative of bacteriochlorophyll. Photosynthesis chemistry, the molecule that green sulfur bacteria use to harvest light. A fish almost certainly can't manufacture that, which means it arrives through the diet, most likely by way of copepods that had been feeding on photosynthetic bacteria. So the dragonfish is borrowing a molecule built to catch sunlight and using it thousands of feet below the last photon of daylight to see a private color. Its close relatives, for what it's worth, seem to have solved the same problem in different ways, which is its own kind of evidence. When several lineages in the same neighborhood are all straining toward red vision, the pressure was real. Think about the sequence that produced that. Prey went dark. Predators went to light. Prey learned to fake light. Predators built a light nobody else could see. Every step in that chain only makes sense as an answer to the step before it, and none of it would exist in a world where prey were easy to find. But the prey side of this had one more move, and it's the one that turns the logic of the whole system inside out. If you're small and something has grabbed you and you cannot fight it, there's still one weapon available. You can make a scene. Here's a thought experiment. You're a tiny animal, you're in the jaws of something bigger, and you have no armor, no venom, no speed left to spend. What's the move? The move, and this is real, is to scream in light. Start with the smallest version. Certain single-celled dinoflagellates, the organisms behind those glowing waves people travel to see, flash when they're jostled. A copepod swimming through a patch of them sets off a trail of blue sparks in the water, the way you'd set off motion lights walking across a lawn at night. For a long time, the obvious question was what the alga gets out of that. Making light costs energy, and it doesn't stop anything from eating you. The answer that experiments have supported is beautifully indirect. The flash works by making the copepod easier to eat. In tank studies, fish hunting copepods do better when the water contains bioluminescent dinoflagellates, because the grazer lights itself up every time it feeds. So the alga's defense runs through a third party. It snitches. Biologists call this the burglar alarm hypothesis. And once you know the name, you start seeing the strategy everywhere in the dark ocean. The most spectacular version belongs to a deep-sea jellyfish called Atolla. It's a flattened red bell with a single long, trailing tentacle, and under normal circumstances, it does nothing dramatic at all. Grab it, though, and it fires. A wave of blue light runs around the rim of the bell, then another, a rotating pinwheel that can go on for seconds and is visible in the black of the deep sea from an enormous distance. There's nothing subtle about it. It is a flare. And a flare is a strange thing for a captured animal to fire, until you work out who it's aimed at. The audience is everything bigger in the neighborhood, and the message is the location of the animal currently holding a jellyfish. The jellyfish's best chance is that something arrives with an interest in eating its attacker, and in the confusion, it drifts away. The oceanographer Edith Witter took that logic and did something clever with it. She built a ring of blue lights that imitates the Atolla alarm, mounted it on a quiet camera platform, and lowered the whole thing into the deep with no bright lights and no noisy thrusters, the usual things that scare off everything you want to film. The idea being that if the alarm really does summon large predators, then faking the alarm should summon them too. It worked. In the Gulf of Mexico, the rig recorded a large squid coming in to inspect a lure that was, in effect, a lie about a jellyfish in trouble. Later, a version of the same approach was part of the effort that finally produced footage of a giant squid alive in its own habitat off Japan in 2012, which is a lovely piece of scientific judo. Human beings had spent a century failing to find that animal by looking for it. What worked was speaking badly, in the language of a jellyfish being eaten. And now flip it one more time, because a signal that summons a predator can also be used by a predator. The cookie-cutter shark is a small thing, a couple of feet long at most, and it makes its living taking round plugs of flesh out of animals hundreds of times its size. Tuna, dolphins, whales. Its belly is covered in photophores, dense and even, doing the standard counter-illumination job. But there's a patch under the throat, a collar that stays dark. Here's the hypothesis, and Witter is among the people who put it forward. From below, that little dark collar hanging in a glowing belly reads as the silhouette of a small fish, something a big predator would rise up to take. The tuna comes in expecting a snack and finds a mouth waiting for it. Nobody has watched that trap spring in the wild, so it belongs in the column marked plausible rather than proven. The anatomy is peculiar enough that it's hard to think of a better explanation. So the arms race in the dark has produced camouflage, an instrument to break the camouflage, a private searchlight, an alarm that calls for help, and possibly a decoy that imitates being small. All of it running on light, in a place where the sun has never once appeared. Which raises the obvious question, why fight over light at all? Why not opt out? Some animals did, and the way they opted out produced the loudest noise made by anything alive. Sound is the ocean's real long-range sense. It travels roughly 4.5 times faster in seawater than in air, and it carries for miles without much loss, which is why the animals that got serious about hunting in the deep abandoned vision as their primary tool and went with acoustics. A sperm whale's head is the extreme case. Somewhere between 1/4 and 1/3 of that whale's entire body is a nose rebuilt into a sound generator. A huge oil-filled complex that takes a pulse of air, snaps it through a set of valves, and focuses the result forward into a narrow beam. The clicks that come out are the most powerful sounds measured from any animal. Reported source levels run up to roughly 236 decibels, referenced to 1 micropascal at 1 meter, which is the standard used underwater. That number can't be compared to a decibel figure you'd see for a jet engine, because underwater acoustics uses a different reference pressure and water behaves differently from air. Within its own scale, though, the point stands. Nothing else alive is louder, and the whale can put a pulse out and read the echo returning from something the size of a squid at ranges that would be useless to any eye. Now, if you were going to design a defense against that, what would you even do? You can't hide behind darkness since darkness is irrelevant. You can't hold still because a stationary object reflects sound just fine. Moths, up in the air, evolved counters to bat sonar, including species that answer a bat's call with ultrasonic clicks that appear to jam it. Nothing like that has ever been documented in the sea, at least not that I'm aware of, and the absence is worth noticing. What the ocean produced instead is a defense of pure materials. An echo happens at a boundary where sound speed and density change. A fish with a gas-filled swim bladder is a superb reflector, because gas and water are wildly different acoustically. That bladder is a beacon, and the squid that sperm whales spend their lives hunting have no swim bladder, no bone, no shell, and a body chemistry that's mostly water with some protein in it. Acoustically, a squid is close to being made of the same stuff as the ocean it's floating in. The echo it returns is faint. Push that further, and you get the gelatinous animals, the jellies and siphonophores and salps, which are so close to seawater in composition that they're nearly acoustically transparent. There's a whole layer of ocean life that toothed whales are probably underestimating, and part of the reason is that it barely shows up on sonar. That's a real defense, and it costs something. Being that watery limits how much muscle you can carry, how fast you can move, how much you can eat. Squid pay for their acoustic quietness with a body that can't be armored, and a handful of fish went the other way and built an ear for the enemy. American shad and some of their relatives can hear well up into the ultrasonic, far above what most fish bother with, and there's good evidence they use it to detect the echolocation of dolphins and bolt before the dolphin closes. They can't stop the sonar. They can eavesdrop on it, which is where the detection stage ends, and it ends without a winner. Every hiding strategy in the ocean has something built to defeat it, and every detection system has something built to slip past it, and the whole thing is still running right now. Nobody's ahead. But finding an animal and reaching it are two completely different problems, and the second one is governed by physics that don't care how good your senses are. Water weighs about 800 times what air weighs. That single fact governs the entire second stage of the hunt, and it's the reason approach is harder in the sea than it is anywhere on land. When a cat stalks a bird, the cat displaces air. Air is thin and compliant, and mostly gets out of the way without complaining. When a fish moves toward another fish, it has to shove a heavy, incompressible fluid aside, and that fluid doesn't quietly disappear. It piles up ahead of the animal in a pressure wall and rolls off along the flanks. Sailors call the equivalent on a boat the bow wave, and every swimming animal has one. So here's the rule that governs everything from here on. In water, moving is broadcasting. There is no such thing as a silent approach. Physics won't allow it, which is why almost every small animal in the ocean carries some kind of flow sensor. The lateral line in fish, antennae in shrimp. In copepods, feathery sensory hairs called setae, standing out from the body into the water, waiting to be bent. Copepods deserve a minute here, because they might be the most consequential animals on Earth that most people have never heard of. They're crustaceans, mostly around the size of a grain of rice or smaller, and by numbers, they are plausibly the most abundant multicellular animals on the planet. They eat the algae. Almost everything else eats them. If copepods disappeared, the ocean's food web wouldn't reorganize, it would collapse. And an animal in that position, hunted by essentially everything, gets very good at leaving. A copepod's escape works like this. The setae detect the deformation of the water around the body, the stretching and shearing that a bow wave produces. When the deformation crosses a threshold, the animal fires. Reaction times have been measured in single-digit milliseconds, faster than the fastest human reflex by a factor that isn't worth calculating because it's embarrassing, and the jump itself reaches speeds of hundreds of body lengths per second. People love to scale that up. If a copepod were the size of a person, it would be going such and such miles an hour. That comparison is nonsense, and I'd rather say so, because muscle power and drag and body size don't scale in a way that lets you do that arithmetic. The honest version is more interesting anyway. For its size, a copepod's escape jump involves some of the highest mass-specific power output recorded from any animal muscle. It is, pound for pound, one of the most explosive movements in biology, and it belongs to a speck of plankton you'd never notice in a glass of seawater. Fish do their own version. Most bony fish have a pair of enormous neurons in the hindbrain called Mauthner cells, and they're built for one job: making a decision fast. Sensory input arrives, and if it's threatening enough, the Mauthner cell fires, and the whole body on one side contracts at once, snapping the fish into a C shape and throwing it sideways out of the path of whatever's coming. That's the C start, and from stimulus to first muscle movement, it can happen in a handful of milliseconds. There's no deliberation in the loop. There isn't time for any. Now hold both of those facts in your head at the same time, because together they create the central problem of stage 2. A huge number of ocean predators feed by suction. They don't bite so much as inhale. Expand the mouth cavity fast enough and water floods in, carrying whatever's floating in it, and the fish closes its jaws around the delivery. It's a superb technique with one fatal weakness. It only works at very short range. The suction field falls off so steeply that beyond roughly a mouth's width away, it does essentially nothing. So a suction feeder has to get its face within about an inch of a copepod that can leave in 3 milliseconds and can feel the predator coming from a body length away. That's a brutal engineering problem, and the animal that solved it best is one nobody would nominate as a great hunter. Seahorses are terrible swimmers. That's a design consequence, and they pay for it. The body is upright, armored in bony rings, and the only real propulsion is a small dorsal fin fluttering away. In open water, a seahorse is close to helpless. And yet, in feeding trials, dwarf seahorses hunting copepods, post-capture rates around 90%, which is a strike rate you almost never see in the ocean. Most predators fail most of the time. Brad Gemmell and his colleagues worked out why, and they did it by filming the water instead of the animal. They seeded the tank with tiny particles and used laser illumination to make the flow visible, so they could watch exactly how the fluid moved as a seahorse approached its prey. The head barely disturbed it. The shape of a seahorse's snout, that long, narrow tube with the small, upturned mouth at the end, creates a region in front of the animal where the water hardly deforms at all. The bow wave, in effect, gets routed around the zone where the copepod sensors are pointed. A seahorse can bring its mouth within a millimeter of a copepod without setting off the alarm. And then the pivot happens. The head snaps upward, and the strike is over in a few thousandths of a second. I find that one of the most elegant results in animal behavior, because of what it says about the shape of the arms race. The seahorse can't outswim the copepod. It can't outreact the copepod. Its entire advantage lives in the geometry of a snout, which is to say, the copepod's defense was defeated by a curve. And notice what the defense forced. That snout is useless for anything else. A seahorse can't chase, can't bite, can't manipulate, can't fight. Every bit of its feeding anatomy has been surrendered to the single requirement of not being felt. That's what a serious defense does to a predator. It adds a weapon, and then it quietly reorganizes the whole animal around that weapon. Other predators solve the approach problem differently, and some of the solutions are more like magic tricks. The trumpet fish is a long, thin fish on Caribbean reefs, basically a swimming pipe. Seen head-on, it's almost nothing, a vertical line, which is already useful. But its best move is social. A trumpet fish will position itself alongside a large, harmless herbivore, a parrotfish or a surgeonfish going about its business, and travel with it, matched to its speed, using the bigger animal as a moving blind. Small reef fish have learned that a parrotfish is safe to ignore. They don't get a vote on what's riding next to it. Cuttlefish do something stranger. Approaching a crab, a cuttlefish will sometimes run a pattern down its arms and body that looks like dark bands flowing forward in a continuous wave. It's called the passing cloud display, and it is hypnotic to watch. The leading interpretation is that the moving pattern interferes with the crab's ability to judge motion, masking the actual approach inside a lot of visual noise. Whether the crab is confused, overloaded, or simply frozen is still argued about. What's not argued is that the cuttlefish is putting on a light show in the seconds before it strikes, and that animals which do that eat well. There's one more solution to the approach problem, and it's the most radical of all. You can decide not to approach. If the problem with approaching is that approaching gives you away, then the cleanest solution available is to make the other animal do the traveling. The deep-sea angler fishes are the famous case, and they're worth looking at closely because almost everything about them is an argument about scarcity. The first spine of the dorsal fin in this whole group has been rebuilt into a fishing rod. It sits on the snout, it can be raised, lowered, and twitched, and at the tip is a fleshy bulb called the esca. Inside the esca, in the species that glow, there's a chamber packed with luminous bacteria. The fish farms its own light, keeping that colony alive in a pouch on the end of a stick in front of its own face, feeding them, venting them, and running them as a bulb. That relationship is stranger than it sounds. The bacteria are picked up from seawater rather than inherited, so every generation of anglerfish has to find and recruit its own light. And the bacterial genomes in those lures show the signs of a partner that has settled in for good, shedding genes it no longer needs, because the fish is providing everything. The lure gets waved. Something small comes to inspect it. And then the anglerfish, which has been essentially motionless, opens a mouth that occupies most of its head. Why does this strategy dominate down there? Because of the accounting. Below about 3,000 feet, food arrives mostly as a slow drizzle from above, the remains of everything living and dying in the sunlit water. It's thin. Deep-sea fish have responded by turning their metabolisms down to a level that's hard to believe from up here. Some deep-living fishes have metabolic rates on the order of a tenth of what a comparable shallow-water fish burns at a similar temperature, and daily food intake for some of them has been estimated at a fraction of 1% of body weight. Individuals can go a very long time between meals. In an economy like that, swimming around looking for prey is a terrible investment. Every stroke costs energy you may not be able to replace. Waiting costs almost nothing. So the deep ocean filled up with animals that converted the entire approach problem into an advertising problem, and then competed on the quality of the advertising. And if you want a measure of how scarce life is down there, look at what anglerfish do about mating. In many ceratioid anglerfishes, the male is a fraction of the female's size, has no functional lure at all, and is mostly a pair of nostrils and a set of gonads. He finds a female by smell, latches onto her with his jaws, and then the tissues fuse. His circulatory system connects to hers. Over time, his eyes and much of his body degenerate, and he becomes a permanent attachment, drawing nutrients from her blood and supplying sperm when needed. Some females carry several. That should be impossible. A vertebrate body normally rejects foreign tissue violently, the way a transplanted organ gets attacked without drugs to suppress the response. Work published in 2020 found that these anglerfishes have lost or degraded key parts of the adaptive immune system, the exact machinery that would otherwise reject the male. They gave up a chunk of their immune defense in order to be able to fuse. Read that as an economic statement, and it's chilling. Encounters are so rare in the deep sea that when a male finds a female, the correct evolutionary answer is to never let go, at any cost, including dismantling the body's ability to tell self from other. That's the environment the lure evolved in. Everything down there is optimized around the assumption that the next opportunity may not come. Up in the shallows, where food is common, the same trick shows up with better production values. Frogfishes are lumpy, slow, thoroughly camouflaged ambush fish that sit on sponges and rubble looking like sponges and rubble. Their lure varies by species, and the mimicry is specific. Some escas look like a small shrimp, some like a worm, some like a tiny fish with what appear to be eye spots and a tail. The frogfish waves the thing with a motion appropriate to whatever it's imitating. A small fish comes over to eat the worm. What happens next is one of the fastest movements any vertebrate makes, and we're going to come back to it in a few minutes. because it belongs to the next exam. Stonefish do it without a lure at all, sitting in reef rubble, encrusted, waiting. Stargazers bury themselves in sand with only the eyes and mouth exposed. And some species have a fleshy flap in the mouth they can wiggle like a worm, while the rest of the animal stays underground. Wobbegongs, the carpet sharks, lie flat with a fringe of skin flaps around the mouth that break up the outline against the reef. All of these solve approach by deleting it. And every one of them pays the same price. An ambush predator eats rarely, so it has to be able to take something large when the chance finally comes. Remember that cost, because it comes due at the very last stage of the hunt, and it's where several of these animals get into serious trouble. Now, lures work because prey animals have to eat. That's the leverage. A fish that ignores every worm-shaped object it sees is a fish that starves, which sets up a slow, quiet contest over how convincing a fake has to be, and there's decent evidence that the pressure runs both ways. Prey species in areas with a lot of lure-using predators tend to be more cautious about approaching small moving objects, and the lures that persist are the ones that stay convincing to a cautious audience. But this whole strategy has a size limit. You can only be a sit-and-wait predator if you're small enough to hide, or if the water is dark enough to hide in. Which raises the question of what you do when you're the size of a car, hunting in clear water, near the surface, in daylight, against prey that is faster and more maneuverable than you are. That's the situation off the coast of South Africa, and the answer is one of the most spectacular things in the ocean. Seal Island sits in False Bay, near Cape Town. It's a small granite outcrop, and it's covered in Cape fur seals, tens of thousands of them, packed onto the rock. Around it, the water drops away into depth. Every morning, the seals have to leave. They can't feed on the island, so groups of them peel off and head out to the open ocean to hunt, and in the evening, they have to come back. Between the rock and the feeding grounds, there's a stretch of deep water that the researchers who work there started calling the Ring of Death, which tells you most of what you need to know. White sharks patrol that ring, and they patrol it deep, 30 or 80 feet down, dark backs against dark water, looking up. That's the whole strategy in one sentence, and it's built on the same asymmetry we saw in the Twilight Zone. From below, the seal at the surface is a clear silhouette against the brightening sky. From above, the shark against the dark bottom is close to nothing. Countershading finishes the job. Dark on top, white underneath, so the animal blends with whatever background it's being viewed against. Now here's the problem that shape solves. A Cape fur seal is a spectacular swimmer. In a straight line it's fast, and in a turn it's far better than a white shark will ever be. A seal can reverse direction in a fraction of its own body length. A shark of that size cannot. If a healthy adult seal sees a white shark coming from 30 feet away with room to maneuver, the seal wins that encounter, and it wins it comfortably. So the shark cannot afford a chase. It cannot afford an approach the seal can see developing. The only version of this hunt that works is one where the seal's advantage never gets to exist. And the way you delete a maneuvering advantage is to delete the time available to use it, which is why the attack is vertical and why it's so violent. The shark accelerates straight up from depth, in the seal's blind zone, on a line where its own silhouette is smallest. By the time it enters the seal's field of view, it's already at full speed and a body length away. And because the water column runs out at the surface, a lot of these attacks carry the shark's entire body clear of the water. A car-sized animal, airborne, with a seal in its jaws. Chris Fallows and Aidan Martin and their colleagues documented hundreds of these events at that one island, and it's from that work that most of what we know about the behavior comes. The details are where the arms race shows. Timing first. The attacks cluster hard into the low-light hours around dawn. In the published observations from Seal Island, success was highest in that dim early window and dropped off substantially as the morning got brighter, which makes sense, since the ambush depends entirely on the shark being invisible until it's too late. Give the seals another hour of light and they start spotting the approach. The seals have read the same data, in the only way animals read data. They cross the ring in tight groups, rather than alone. They travel fast, porpoising, taking low flat arcs that keep them near the surface, where a vertical attack has less room to build speed. Young seals, the inexperienced ones, are disproportionately the ones that get taken. And seals that do survive the initial strike will sometimes do something that looks insane and is actually smart. They stay very close to the shark, right at its flank or behind the tail. In the one region where a shark that turns by bending its whole body simply cannot reach. That's the fingerprint of a real arms race. The prey isn't just running. It's exploiting a specific known limitation in the predator's turning geometry, and the numbers reflect it. Across the observations at that site, a good share of attacks failed, roughly half in the seasons that were carefully scored. That's the thing people get wrong about big predators. The successful hunt is the exception being filmed, and the ordinary experience of a white shark is missing. There's a broader point in there, and it's one of the reasons this stage matters more than the strike itself. Every ambush is a bet that the target hasn't noticed yet. Once the target notices, the entire physical advantage flips, and it flips instantly. A great white that has been seen at 40 feet has already lost, which is why some predators stopped relying on stealth and started rearranging the environment instead. In Antarctic waters, there's a type of killer whale that hunts seals resting on floating ice. A seal on an ice floe is effectively safe from a swimming attack, so the whales don't attack it. They swim away from the floe in a line, side by side, then turn and come back together, accelerating just under the surface. And at the last moment, they dive. The wall of water they've pushed keeps going. The wave breaks over the floe and washes the seal off, or breaks the ice apart. Sometimes it takes several attempts, with the whales coordinating, repositioning the floe by pushing it into open water first so there's room to build the wave. Bob Pittman and John Durbin documented this in detail, and one of the things they recorded is that the whales appear to work on the floe strategically, trimming it down over successive passes. That's an engineering solution to a defense that had nothing to do with fighting. No bigger jaw involved, no faster body. Bottlenose dolphins in the shallow flats of Florida do a smaller version. A single dolphin will swim a tight circle in the soft bottom, beating its tail to lift a curtain of mud into the water. Fish inside the ring will not swim through the mud wall. They do the one thing available to them, which is to jump. And the rest of the dolphins are waiting on the outside of the ring with their mouths open, facing in. The fish are being persuaded to deliver themselves by a barrier made of nothing but suspended sediment. Every one of these techniques exists because the direct approach stopped working. And nowhere did the direct approach stop working more completely than against the single most common defense in the entire ocean, which is one that has no anatomy at all. A school of fish is a defense made entirely out of other fish. It has no shell, no spines, no venom, no speed beyond what a single fish already has. And it works so well that roughly a quarter of fish species are thought to shoal their entire lives, with about half doing it at some stage of life. 3 things are going on at once inside that ball of sardines. The first is arithmetic. If a predator eats 1 fish per attack, being in a group of 50,000 means your personal odds on any given attack are 1 in 50,000. Biologists call it the dilution effect, and it's the least glamorous and most reliable of the 3. The second is surveillance. 50,000 fish means 100,000 eyes covering every direction at once, and information moves through a school astonishingly fast. When one fish on the edge starts a turn, the wave of movement can propagate across the group faster than the individual fish could each react to the predator on their own, because they're reacting to each other. You've seen the footage. A school turning looks like a single sheet of metal flexing. The third is the interesting one, and it's the reason so many weapons in the previous section exist. It's called the confusion effect, and it's a real measurable failure in the predator's brain. To catch a fish, you have to select a fish. You need to lock onto one target and predict where that target is going to be when your mouth arrives. And a mass of identical fish moving in overlapping paths wrecks that process. Experiments going back decades have shown the same pattern. As group size goes up, the attacker's success rate per attack goes down, even when there are more targets available than the predator could possibly need. Think about how strange that is. The prey has made itself more visible. A silver ball of thousands of fish in open water is the single most conspicuous thing in the entire ocean, and it is safer than one anchovy alone. That defense works by overwhelming the targeting system. Hiding has nothing to do with it. So how do you beat that? Every solution comes down to the same insight. Stop trying to pick a fish out of a school and change the school instead. The first move is compression. Predators from tuna to sea lions to dolphins to gannets will work a school from the outside, driving it upward and inward until it forms a tight ball at the surface. The surface matters because it's a wall. A fish in open water has 3 dimensions to escape into. A fish at the surface has 2.5. That's the setup. And it's cooperative in a way that crosses species lines constantly. Off South Africa, during the sardine run, you'll get common dolphins, Cape gannets, sharks, tuna, and whales working the same bait ball. And while they're not cooperating in any warm sense, they're each making the ball tighter for everyone else. Now the weapons. The sailfish is built around the confusion problem. That bill, the long, rigid spear on the front of its skull, is not primarily a lance for skewering, and studies that filmed sailfish attacking sardine bait balls found something more surgical going on. The fish slides its bill into the edge of the school slowly, so slowly that it doesn't trigger the school's flight response, and then it accelerates the bill sideways in a hard slash, no specific target required. The slash sweeps a whole plane through a crowd. What that does is produce injuries. A sardine that takes a hit from the rough surface of a sailfish bill is slowed, or knocked off course, or scaled. And the researchers who scored these attacks found that most individual slashes didn't produce a capture at all. What they produced was accumulating damage across the school. Sardines got progressively more injured over the course of an attack, and captures came from the damaged fish, the ones that could no longer hold formation, which reframes the whole weapon. The bill's job is to convert a coordinated group into a collection of individuals, one of whom is now slower than the rest. It defeats the confusion effect by manufacturing an exception. The pelagic thresher shark does the same job with different hardware, and the hardware is ridiculous. Roughly half the length of a thresher shark is tail. The upper lobe of the caudal fin is enormous, longer than the entire rest of the animal in some individuals, and for a long time nobody was certain what it was for. Fishermen had claimed for a century that threshers hit fish with their tails. Science didn't have footage. Then a team led by Simon Oliver filmed pelagic threshers hunting sardines off Pescador Island in the Philippines, and the fishermen turned out to be right in a way nobody expected. The shark swims into the school, then brakes hard with its pectoral fins, and pitches its body downward while whipping the tail forward over its own head. The tail tip travels far faster than the shark itself because the whole body has acted as a lever to accelerate it. The lobe sweeps through the school like a bullwhip. In the footage, sardines are stunned outright, several at a time from a single slap. Some are killed. The shark then turns around and eats the ones drifting motionless in the water. Multiple prey, one motion, no targeting problem to solve. The confusion effect only protects you if the predator has to choose. This animal has stopped choosing. Killer whales in Norway run yet another version on herring, and theirs is the most obviously organized. Groups of whales herd herring into a dense ball near the surface, working around it using flashes of their white undersides to keep the fish packed. Then individual whales come in and slap the ball with the underside of the tail fluke. The shockwave stuns or kills a batch of herring at once, and the whale turns and picks them off one by one as they sink. Researchers using acoustic tags on these whales found that the overwhelming majority of feeding events they could document were associated with a tail slap. Whole body attacks, just swimming in and grabbing, were the small minority. It's more efficient to hit the school than to chase the fish. Look at what all three of those weapons have in common. The sailfish bill, the thresher's tail, the killer whale's fluke, different animals, different oceans, different body plans, and every one of them arrives at the same answer. Use an extended limb to strike an area instead of a point. The school made individual targeting fail, so predators stopped aiming at individuals. And that's the second exam. Detection tells you where. Approach gets you there. But all of it so far has been preparation. And preparation is cheap compared to what happens next, because now the predator has to actually touch the prey, and touching is where the ocean's real engineering shows up. Muscle has a ceiling, and it's worth understanding why, because that ceiling is the reason some of the ocean's weapons look the way they do. A muscle produces force by shortening. The catch is that the faster a muscle shortens, the less force it can produce. Push for maximum speed, and you lose power. Push for maximum force, and you lose speed. Every animal that has ever tried to move fast has run into this, and there's no way around it as long as muscle is doing the moving. So a bunch of animals stopped letting muscle do the moving. The trick is to separate the loading from the release. You use slow, powerful muscle to deform a spring gradually, over as much time as you like. Something holds that spring compressed, a latch. Then the latch lets go, and all the energy you spent seconds putting in comes out in a couple of thousandths of a second. Engineers would call it a crossbow. Biologists call the general design a latch-mediated spring, and it shows up independently all over the tree of life, in trapjaw ants, in the tongues of chameleons, in the jaws of certain fish. The most spectacular version lives in a hole in a coral reef and is about the size of your hand. Mantis shrimp are stomatopods, not shrimp, and the group splits into two functional camps that are the cleanest illustration of this entire video's argument that I know of. One camp, the Smashers, has a pair of raptorial appendages folded under the head that end in a heavy calcified club. The other camp, the Spearers, has appendages that end in long barbed spines. Smashers eat snails, crabs, clams, and hermit crabs. Spearers eat fish and shrimp. That's it. That's the whole explanation for the difference. One group faces prey defended by armor, so it evolved a hammer. The other faces prey defended by escape speed, so it evolved a harpoon. Put the two weapons side by side, and you can read off, with no other information, what each animal has been fighting. The numbers on the hammer are what put mantis shrimp on the internet. Sheila Patek and her colleagues published the measurements in 2004, filming peacock mantis shrimp with high-speed cameras. The club reaches peak speeds around 23 meters per second, which is about 50 miles an hour, and it gets there in under 3/1000ths of a second. Peak accelerations came out on the order of 100,000 meters per second squared, which is roughly 10,000 times the acceleration of gravity. Later work measured peak forces well over 1,000 times the animal's own body weight. That's already absurd. And then the water does something extra. At those speeds, the club outruns the fluid's ability to fill in behind it. The pressure in the water drops below the vapor pressure, and the seawater flashes into a bubble of vapor right in the gap between the club and the target. A fraction of a millisecond later, that bubble collapses, and when a cavitation bubble collapses, it does so violently, releasing a pulse of pressure, heat, and a flicker of light. so the snail gets hit twice. Once by the club and once by the water. The strike is fast enough that the club actually gets damaged doing this, and the animal's answer is one of the reasons materials scientists keep showing up at stomatopod labs. The club is built in layers, with a hard outer surface over a region where fibers are laid down in a spiraling, gradually rotating arrangement. That structure blunts cracks, forcing them to travel a longer and more difficult path. The mantis shrimp built a hammer that manages its own fracture mechanics, and people are now trying to copy the architecture for body armor and aerospace panels. Aquarium keepers will tell you these animals crack the glass of their tanks. That's reported often enough by enough people that I'm inclined to believe it happens, though it's the kind of claim that lives in hobbyist forums rather than journals. What is measured is that they routinely destroy the shells of prey animals whose entire defensive strategy is being too hard to break. That opens the deep time version of this story, and it's my favorite piece of context in the whole subject. If you go back far enough in the fossil record, seashells look different. Through the Middle and later Mesozoic, the era of the dinosaurs, marine snail and clamshells in the record shift toward thicker walls, tighter and narrower openings, more ribs, knobs, and spines, and more of them burrowing into the sediment instead of sitting on top of it. Over the same interval, the animals capable of crushing shells diversify. Certain crabs, certain fish, raise with pavement-like grinding teeth. The paleontologist Gerard Vermeij named this the Mesozoic Marine Revolution and argued it was an arms race, written into the rock, with prey escalating armor as predators escalated crushing power. It's a hugely influential idea, and it's still argued over, since fossil patterns can be produced by other things, including changes in climate, ocean chemistry, and what got preserved. Other researchers have proposed that some of those shell changes have more to do with reproduction or environment than with predators. Even with the debate, the core observation stands on its own, and it's worth saying plainly. Armor and the tools for breaking armor got more extreme together. Over tens of millions of years. Neither one makes sense without the other. Now, if you're small and you can't build a club, there's another way to hit something at range. And one animal does it with a bubble alone. Snapping shrimp are small, common, and if you've ever put a hydrophone in warm, shallow water, you've heard millions of them at once. The sound is a continuous crackle, like frying bacon. And during the Second World War, it was loud enough over some reefs and shell beds that it interfered with sonar operations. Submarines are said to have used shrimp beds as cover. Whole naval acoustics programs went into figuring out what the noise was. The noise is a claw. One of the shrimp's claws is grotesquely oversized, sometimes half the animal's body weight, and it's built as a plunger and socket. The shrimp cocks it open, held by a catch, with muscle slowly loading the joint. When the catch releases, the plunger slams into the socket and squirts a jet of water out of the claw at very high speed. For decades, everyone assumed the bang was the two halves of the claw hitting each other. In 2000, a team of physicists in the Netherlands, working with high-speed video and hydrophones together, showed that's wrong. The claw halves make almost no sound. What makes the sound is the water. The jet moves fast enough to drop the local pressure below the point where seawater holds together, so a cavitation bubble forms in the wake of the jet. The bubble grows, then collapses. The collapse is the bang, and it's a proper bang. Snapping shrimp are among the loudest animals in the ocean by peak pressure, which is a ludicrous sentence to write about something that weighs less than a paperclip. The following year, the same group reported something even odder. When that bubble collapses, there's a brief flash of light. They called it shrimpoluminescence. The interior of a collapsing bubble gets extremely hot for an extremely short time, with estimates running into the thousands of degrees, though the uncertainty on those estimates is large, and the volume involved is microscopic. Nothing around the shrimp warms up in any way that matters. For a few billionths of a second, though, in a bubble smaller than a grain of sand, conditions get extreme. Now, why does an animal do this? Because it turns a grab into a shot. A snapping shrimp uses the pressure pulse to stun or kill small fish and other shrimp at a short distance, and it also uses it to fight off rivals and to warn away intruders from its burrow. Look at that from the prey's side. Small reef shrimp and small fish are protected by exactly the things we've been discussing. Flow sensors, fast escape reflexes, a body that can be somewhere else in 3 milliseconds. All of those defenses assume the threat is a physical object that has to travel to you. A pressure wave doesn't travel at swimming speed. It travels at the speed of sound in water. The escape response is fast, and it's still hopeless because it starts after the weapon has already arrived. That's what makes it such a clean example. Nothing about that defense was outrun. It was made irrelevant by a weapon operating in a different physical regime altogether. Now back to a debt I left open a while ago. The frogfish, sitting on its sponge with a lure waving in front of its face. A small fish comes in to inspect the fake worm, and then the frogfish opens its mouth. The mouth expansion is enormous, several times the resting volume of the head, and it happens so fast that the water outside can't get out of the way. Everything in front of the frogfish, including the fish that came to investigate, gets pulled in with the inrushing water. Measurements of that strike put it at around 6,000ths of a second from start to finish, which is among the fastest feeding movements recorded in any vertebrate. 6 milliseconds. Remember the numbers from earlier. A fish's fastest escape reflex, the Mauthner cell C-start, needs a handful of milliseconds just to get the first muscle contraction going. The frogfish strike is finished inside the prey's reaction window. By any ordinary standard, the victim's escape system is fast. It has simply been outrun by a movement designed against its specifications. There's a variation on this that solves the approach problem and the strike problem in one motion, and it belongs to a reef fish that looks completely unremarkable until it feeds. The sling jaw wrasse has a jaw apparatus that, when it fires, shoots the whole mouth forward on a set of hinged bones, extending a tube out in front of the face. The protrusion can reach something like 2/3 of the length of the fish's head, which is the most extreme jaw extension known in fishes. The wrasse hovers, sights a shrimp tucked into the coral, and the mouth leaves the face and goes and gets it. That's a direct answer to the bow wave. To bring a mouth within suction range, the most fish have to bring the body, and the body announces itself. The sling jaw sends the mouth alone, and the rest of the animal stays put, generating far less of a warning than a lunge would. Every one of these solutions costs something. The frogfish is a slow, awkward, poorly swimming animal that has invested its whole body plan in one enormous mouth. The sling jaw's feeding apparatus is a complicated linkage of thin bones that limits what else the jaw can do. The mantis shrimp has to spend real time reloading its spring between strikes. Specialization is expensive. Prey defenses made it necessary anyway. But all of this assumes you can generate speed at all. What if you can't? What if you're a snail? Cone snails are snails. That's the whole premise. They crawl slowly. They have a shell that people collect because it's beautiful, and several hundred species of them hunt live prey. Some eat worms. Some eat other snails. And some of them eat fish. Take a second on that. A snail that catches fish, the weapon is a tooth. Snails have a radula, a ribbon of tiny teeth used for rasping algae off rocks. And in the cone snails, a single radular tooth has been rebuilt into a hollow, barbed harpoon. The snail keeps a magazine of them. It loads one at a time into a flexible proboscis, and the proboscis can extend well out from the shell. When a fish comes within reach, the harpoon fires, embeds, and injects. What it injects is where this gets remarkable. Cone snail venom is a cocktail of small peptides called conotoxins, and a single species may produce dozens or even hundreds of distinct ones. They're not variations on a theme. Different conotoxins target different ion channels and receptors in the victim's nervous system, and the snail deploys them in coordinated groups that researchers have nicknamed cabals because they work together toward one outcome. The fastest of these is exactly what a snail needs. A fish that has been harpooned by certain cone species goes rigid almost immediately because a set of toxins arrives that keeps sodium channels from shutting off, and every nerve fires at once and stays fired. The fish is locked in place before it can complete a single tail beat. Now think about why that's necessary. A snail cannot pursue anything. If the fish swims 10 feet away and then dies, the snail gets nothing. The harpoon has to convert a mobile animal into an immobile one in the time it takes to twitch, or the entire investment is wasted. The venom's speed is a direct consequence of the hunter's slowness. And then there's Conus geographus, which does something that sounds made up. This species doesn't harpoon a swimming fish first. It approaches sleeping or resting fish and unfurls an enormous, flexible mouth, a wide funnel, that it drapes over the target like a net. And before that, it releases a plume of chemicals into the water around the fish. In 2015, a team led by Helena Safavi Hamami published what's in that plume, and part of it is insulin. Actual insulin, or a close relative of it, structurally similar to fish insulin rather than to the snail's own. The venom insulin drives the fish's blood sugar down. A fish swimming into a cloud of it goes sluggish and disoriented, and researchers watching this describe the prey as being sedated before the snail ever touches it. A snail is using a hormone as a chemical weapon. It has weaponized the endocrine system of an animal it can't catch. I don't know a cleaner example of what pressure does to a lineage. Cone snails could not solve the speed problem, so they stopped trying to solve the speed problem and went after the fish's metabolism instead. Two practical notes, because this is one of the few places in this video where the biology touches human safety directly. The geography cone is dangerous to people. Human deaths from cone snail stings are rare but documented, and there is no anti-venom. The rule is simple, and it has no exceptions worth debating. Don't pick up live cone snails and treat any cone-shaped shell in shallow tropical water as potentially occupied, because you can't tell from the outside. If someone is stung, that's an emergency room situation immediately, not a wait-and-see one. The second note is more cheerful. Because conotoxins are so precisely targeted, they've turned out to be valuable in medicine. A synthetic version of a peptide from a different cone species is an approved drug for severe chronic pain in patients who can't be managed otherwise. It's a real medication derived from a snail's hunting kit. Now, cone snails at least have a nervous system and a plan. The animals with the fastest weapon in the ocean have neither. Every jellyfish, every sea anemone, every coral polyp, every one of the hundreds of thousands of individual animals in a siphonophore chain is armed with the same device, the nematocyst, a stinging capsule built inside a single cell, sitting just under the surface with a trigger hair exposed. Inside the capsule is a coiled, hollow thread, often barbed, and the capsule fluid is held at an internal pressure that's hard to picture at that scale. When the trigger is set off, the capsule opens and the thread turns inside out and shoots outward. The measurements come from work published in 2006 on Hydra, a small freshwater relative, and they're worth quoting carefully because the numbers are outlandish. The discharge completed in about 700 billionths of a second. The accelerations the researchers calculated ran into the millions of times the acceleration of gravity. The pressure the thread's tip exerts on impact was estimated in the range of gigapascals, which is comparable to the pressures used in industrial cutting. That's from a freshwater animal in a lab, and marine species will differ in the details. The mechanism is shared across the group, though, and the design principle is the same everywhere. Here's what makes it the perfect weapon for the animal carrying it. A jellyfish has no brain. It has a nerve net, no central processor, no eyes in most species, and muscle that's only good for slow pulsing. It cannot aim. It cannot decide. It cannot chase a copepod. And a copepod could leave 100 times over in the time a jellyfish takes to do anything at all. So the pneumaticist isn't aimed by the jellyfish. It's triggered by the victim. Contact does it. The prey animal fires the weapon by touching it. And once fired, the discharge is over faster than any nervous system on Earth can register, which means an escape reflex is meaningless. There is nothing to react to. The reaction would arrive tens of thousands of times too late. That's how an animal with no brain routinely catches animals with excellent ones. Box jellyfish took the design further and added the parts everyone assumed a jellyfish couldn't have. Species in that group carry clusters of eyes, including eyes with real lenses and retinas, and they swim actively and steer. Their venom acts on the cardiovascular system with terrible speed. For people, the Australian box jellyfish is among the most dangerous animals in the sea, and the correct response is the boring one. Obey local beach closures and stinger net seasons. Wear protective clothing where authorities recommend it, and treat any serious sting as an emergency requiring professional medical help rather than a home remedy. And venom keeps appearing wherever a predator lacks the strength to win a fight. The blue-ringed octopus is smaller than a golf ball with the arms out, and it hunts crabs, which are armored and have claws, and outweigh it. Its saliva carries tetrodotoxin, produced by bacteria the animal hosts. The octopus can simply deliver the toxin and wait. A crab that would win any wrestling match loses to a chemical it never had a defense against. Blue rings, by the way, are a warning signal. The octopus flashes them when it feels threatened, which is the animal politely telling you the thing you most need to know. So that's the third exam. The strike gets landed by speed, by geometry, by pressure, or by chemistry. And in every case, the method is a mirror image of the specific defense it had to beat. And now we get to the part of this that nobody makes documentaries about, which is a shame because it's where most of the failures happen. You've got the animal. It's alive. It's touching you. And it wants to leave. Grip is the ocean's forgotten problem, and it's a much bigger one than it sounds. Think about what a predator is actually holding at the moment of contact. A wet animal, covered in mucus, in most cases, because fish coat themselves in slime for reasons unrelated to predators, and it turns out to work beautifully against them. Streamlined, so there's nothing to catch on, muscular, and now using every fiber of that muscle at once because a fish in a mouth is producing the most powerful contraction of its life, and surrounded by water, which is a lubricant. On land, a predator can pin prey against the ground. That option barely exists in open water. There's nothing to press against. Every force you apply pushes you backward, as much as it pushes the prey forward. So the sea had to invent grip from scratch several times, and the results are some of the most specialized structures in vertebrate anatomy. Start with teeth, because teeth are where people assume the story is about damage, and mostly it isn't. Look at the teeth of a barracuda, a moray, a viperfish, a deep-sea anglerfish. They curve backward, every one of them. That curve is the entire point. A backward curving tooth slides in easily on the way through, and then resists coming out. When the prey pulls away from the mouth, the geometry converts that pull into deeper penetration. The harder it fights, the more thoroughly it's held. It's a ratchet. The prey's own escape effort operates the mechanism, and in the deep sea, where a meal might be the only one for weeks, that logic gets pushed to its extreme. The fang tooth is a small, blunt, ugly fish, no longer than your hand, and it carries the largest teeth relative to body size of any fish in the ocean. The lower fangs are so long that the animal physically cannot close its mouth around them, An evolution solution is a pair of sockets in the roof of its skull, on either side of the brain, that the fangs slide into when the jaw shuts. Look at the design constraint that implies. This fish had to remodel its own brain case to make room for its teeth. That happens when losing a captured meal is a survival-level failure. Viperfish do something similar, with fangs long enough to sit outside the mouth entirely, curving up past the eyes. In that group, the first vertebra behind the skull is modified in a way that appears to help absorb the shock of the strike, because when you strike with your face, your neck has to survive it. A fangtooth's fangs would be a poor tool for slicing anything. What they are is a cage that closes around an animal in the dark and doesn't open. Now teeth alone still leave a problem, and it shows up in a fish that everybody recognizes and almost nobody understands. Morays live in holes. That's their entire ecological identity. They hunt in the tightest parts of the reef, in crevices and under coral heads, which is precisely where small reef fish go to be safe. So the moray is doing what predators do, attacking the defense directly. The problem is that hunting in a hole breaks the standard fish feeding system. Almost every bony fish moves prey from the mouth to the throat with water. The mouth opens, the head expands, prey and water rush in, and then the fish closes its mouth and pushes water back out over the gills, while the prey gets carried backward on that flow. It's a hydraulic conveyor belt. It's also the whole reason fish can swallow at all. Try running that system inside a coral crevice. There's no room for the head to expand. No clean flow path. No space for the water to go. Suction feeding needs open water, and a moray spends its life somewhere else. So a moray does the only thing it can. It bites. And then it's holding a live fish in its front jaws with no functional way to move it backward, which is a properly stuck situation. And it's the kind of problem that usually ends with the prey escaping. In 2007, Rita Mehta and Peter Wainwright published what morays actually do, and the answer had been hiding inside the animal the whole time. Fish have a second set of jaws. Almost all bony fish do. They're called pharyngeal jaws. They sit back in the throat, and they're normally modest structures used for grinding or manipulating food that has already arrived. In morays, they're enormous. They carry curved teeth, and they are mounted on muscles that let them travel. When a moray has prey in its front teeth, the pharyngeal jaws launch forward, out of the throat, into the back of the mouth. They clamp onto the prey. Then they pull backward, dragging the fish down the throat, and release, and go forward again if needed. A second mouth, coming up out of the neck to grab the food and pull it in. The obvious comparison has been made 1,000 times, and I'll spend one sentence on it. Yes, it's the creature from the movie, except the movie came first, and the biologists found the real version afterward. What matters more is the causal chain. Small fish hid in holes. Morays followed them into holes. Holes made suction feeding impossible, so the throat evolved into a grabbing arm. The prey's hiding place reshaped the predator's neck. That's how specific this stuff gets. Morays have one more trick for the same problem, and it's the low-technology one. Faced with something too large to pull in whole, a moray will bite down, then tie its own body into a knot, slide the knot forward against the prey, and use it as leverage to twist and tear. It's using its body as a fixed point in a medium that doesn't provide any, which is the underlying theme of this entire stage. On land, you brace against the earth. In the ocean, if you want something to push against, you have to bring it with you. Vertebrates solved grip with teeth. A completely different branch of the animal kingdom solved it with something better. And it's the reason cephalopods punch so far above their weight in the ocean's food web. An octopus arm has no bones. It's a muscular hydrostat, the same construction principle as your tongue or an elephant's trunk, a solid mass of muscle arranged in 3 directions that can stiffen, bend, elongate, shorten, and twist at any point along its length, and can form a joint anywhere it wants one. There is nothing comparable in a vertebrate limb. Your arm bends in the places the skeleton allows. An octopus arm bends wherever it decides to. Along that arm sit the suckers, and the suckers are the part worth slowing down for. A sucker is a muscular cup. It seals against a surface, and then muscles pull the roof of the cup upward, increasing the volume of the sealed space. Since no water can get in, the pressure inside drops, and the ambient pressure of the ocean presses everything together. That's the whole mechanism, which sets a physical ceiling on how hard a sucker can pull. And the ceiling is interesting. At the surface, the maximum pressure difference you can generate is limited by the atmosphere plus the water above you. And before you reach it, the water inside the cup starts to boil at room temperature, forming vapor which breaks the seal. That's cavitation again, doing the opposite favor this time. Go deeper though, and the ambient pressure rises, and the ceiling rises with it. A deep living cephalopod can generate far greater adhesive force before cavitation sets in than a shallow one can. The depth an animal lives it partly determines how strongly it can hold on. And octopus suckers do more than hold. Work published a few years ago identified receptors in the sucker rim that respond to chemicals on contact, a sense that sits somewhere between taste and touch. An octopus reaching blindly into a crevice is tasting the inside of the hole with its skin, sorting food from rock without ever seeing either. Squid, hunting in open water instead of on the bottom, needed something harsher, because a fish in open water can accelerate away from a soft cup. So squid suckers carry rings of chitin around the rim, and in many species those rings are toothed, a circle of small hard points that bite into the prey's skin while the suction holds. Some groups went further and abandoned suction on the feeding tentacles entirely. In the hooked squids and in the colossal squid of the Southern Ocean, suckers on the tentacle clubs have been rebuilt into hooks, and in the colossal squid some of those hooks swivel in their sockets. Picture the sequence. 2 tentacles fire out, longer than the rest of the arms, and the clubs at the ends catch a fish. Hooks rotate into it. The fish is drawn back into a crown of 8 arms lined with toothed rings, and the harder it pulls, the more of those rings engage. That's the same ratchet principle as the moray's backward teeth, arrived at by an animal with no skeleton and no teeth at all. Sperm whales carry the evidence of the other side of that exchange. Whales in some populations are found with circles of scar tissue on the head and around the mouth, and those marks are attributed to squid sucker rings and hooks scraping across skin during a struggle. It's a fight the squid loses, and it clearly makes the whale work. That claim gets stretched, though. The size of the largest scars has been used to argue for squid bigger than anything ever landed, and skin scars grow along with the whale that's carrying them. The scars are real. The inferred giants are an inference. Behind the arms, cephalopods have one hard part, and it's a beautiful piece of engineering. The beak looks like a parrot's, and it's made of chitin and protein, with no mineral in it. Here's the problem it has to solve. A beak that's hard enough to cut through fish and crustacean shell would ordinarily tear its way straight out of the soft muscular tissue that holds it. The way a razor blade pushed into gelatin does nothing but destroy the gelatin. The solution, published by Ali Miserez and colleagues, is a gradient. The tip of the beak is extremely stiff. The base, where it's anchored in muscle, is soft and pliable. And the transition between them runs continuously through the material, with the composition changing gradually rather than at a boundary. So there's no sharp interface for stress to concentrate at. Materials scientists have been trying to copy that ever since because joining hard things to soft things without a weak point is a problem. Human engineering has never fully solved. Behind the beak sits the radula, the same rasping tooth ribbon we met in the cone snail. And octopuses use it for something that turns grip into a completely different kind of weapon. An octopus that finds a clam or a snail it can't pull open has a procedure. It holds the shell, positions it, and drills. The radula works a small hole through the shell, and in some species, a secretion helps soften the shell material at the drill site. Through that hole, the octopus injects a paralyzing agent from its salivary glands. The muscle holding the shell closed relaxes. The shell opens on its own. Look at what happened there. The prey's defense is a sealed container operated by a muscle. The octopus can't break the container and can't outpull the muscle, so it drills a hole the size of a pinprick and turns off the muscle from the inside. That's the pattern that keeps repeating in this stage. Where grip alone can't win, the winning move is to attack the thing that's generating the resistance. And that principle reaches its purest form in a bivalve, a sea star, and the slowest fight in the ocean. A muscle has one defense. It closes. That sounds pathetic, until you look at how it closes. The adductor muscle that pulls the two shells together contains a special kind of muscle tissue, built around a protein called paramyosin, that can enter what physiologists call the catch state. In catch, the muscle locks. It maintains tension for hours, or for days, at a tiny fraction of the energy cost of holding a normal contraction. That's a superb piece of engineering. So let me put it in terms you can feel. Hold your arm out straight in front of you. Now hold it there for 6 hours. You can't, and the reason you can't is that your muscle is burning fuel the entire time to maintain that position. A muscle's adductor essentially throws a bolt. The energy cost of staying shut drops to almost nothing. Against a crab trying to crack it, that works. Against a fish trying to bite it, that works. Against almost every predator in the ocean, a locked shell is the end of the conversation. Then the sea star arrives, and the sea star has all the time in the world. The underside of a sea star's arms is covered in hundreds of tube feet, each one a small hydraulic cylinder run off a water-filled canal system inside the animal. They're often described as suction cups, and that's not quite the story. The tip of a tube foot secretes an adhesive that glues it to the surface, and then a second secretion releases the glue when the animal wants to let go. It's a chemical grip, made and unmade thousands of times as the animal walks. Individually, a tube foot pulls almost nothing. There are hundreds of them. The star humps itself over the muscle, gets a grip on one valve with the feet on some arms and the other valve with the feet on the rest, and then it pulls. Steadily. Not in bursts. And it holds that pull for hours, cycling individual feet on and off, so that the total force never stops, while no single foot has to work continuously. And now comes the detail that makes the whole story work, the one most people miss. The sea star doesn't have to open the shell. It has to open a gap of a fraction of a millimeter, narrow enough that you'd struggle to see it, is enough, because what the sea star does next has no size requirement at all. It pushes its own stomach out through its mouth. Sea stars avert the cardiac stomach, turning it inside out through the mouth on the underside of the body, and slide it through that hairline gap into the space between the shells. Digestive enzymes go to work on the muscle, while the muscle is still alive and still, as far as it knows, successfully closed. The muscle keeping the shell shut is itself being digested. There's no moment of violence in that whole sequence. There's no strike, no chase, no venom. It's a slow, patient, chemical defeat of a defense that was designed to outlast attacks. And the reason it works is worth stating plainly, because it's the counterintuitive lesson of this entire stage. The catch mechanism makes the muscle cheap to defend and hard to break. What it can't do is beat an opponent whose only technique is refusing to stop. The muscle's defense has a limit measured in hours. The sea star measures in hours too, and it has fewer other things to do. Now, a completely different way to solve the holding problem: give up on holding the whole animal. The cookie cutter shark is roughly the length of your forearm. Its targets include tuna, dolphins, seals, and whales, animals that outweigh it by factors in the thousands. It has no chance of subduing any of them. It has no chance of holding one. In any conventional predator-prey framing, this is an animal that should be starving. Its solution is to redefine what counts as catching something. The mouth is built as a seal. Fleshy lips create suction against the target's skin, locking the shark in place. The teeth of the lower jaw are large, triangular, and interlocked at their bases into one continuous cutting band. The upper teeth hold. The lower blade cuts. Then the shark rotates its whole body. The result is a clean, round, conical crater, a couple of inches across, cut out of an animal that will survive the encounter and probably didn't stop swimming. Whales in some populations are covered in these healed circular scars, dozens of them, a lifetime of small deposits taken by something they never saw. It's parasitic in shape, though the shark isn't attached for more than a moment. And it defeats the single most effective defense in the ocean, which is being enormous. Size protects you from being eaten. It does absolutely nothing to protect you from being sampled. Cookie cutters have taken bites out of things that aren't animals too, including the soft sonar domes of research submarines back in the 1970s, which caused real problems until the material was changed. Something about the shape and the rubber apparently reads as edible. Killer whales solved the the holding problem in the most cognitive way available, which is by using something they know about the prey's nervous system. Sharks and rays can be put into a state called tonic immobility. Invert a shark, hold it belly up, and it goes limp and unresponsive, breathing shallowly, for a period that can last several minutes. Researchers use it to handle sharks without sedation. Nobody is completely sure what it's for, evolutionarily. Killer whales use it. There are documented cases of orcas flipping sharks and rays upside down and holding them there, and the shark stops fighting. In South Africa, the pair of killer whales that became notorious for preying on white sharks appear to work along the same lines, immobilizing an animal that could otherwise do them serious damage. A predator has found a bug in another predator's operating system and is exploiting it deliberately. That's a strange thing to say about a whale, and it's the most economical explanation of the footage. Finally, the failure case, because this whole stage deserves an example of the predator losing. Hagfish are jawless, eel-shaped, ancient, and famously unlovely. They live on the bottom, and their defense against being bitten was documented on camera off the coast of New Zealand by Vincent Zinsen and his colleagues, using baited cameras on the seafloor. Across their footage, hagfish were attacked 14 times by sharks, conger eels, wreckfish, and a range of other predators. In every single one of those attacks, the hagfish survived. What it does is release slime. Hagfish slime is a suspension of thread cells packed with coiled protein fibers that unspool on contact with seawater and expand in a fraction of a second into a mass of gel thousands of times the volume of what was released. A hagfish can turn a bucket of water into something with the consistency of egg white in under a second. Fired into the mouth of an attacking predator, it goes into the gill chamber. And the footage shows exactly what happens next. The attacker releases the hagfish immediately and starts convulsing its gill arches, gagging, working to clear its own breathing apparatus. Every one of those predators had won the detection stage, won the approach, and landed a successful strike. They lost at grip, and they lost badly enough that the hagfish swam away. 14 out of 14. That's about as decisive as animal behavior data gets. So a predator can find the animal, reach it, hit it, and hold it, and still have one exam left. And the last one is the strangest, because on paper, it shouldn't be difficult at all. Swallowing sounds like a formality. It is the single most reliable way for an ocean predator to die. The reason is that the last stage of a hunt is where the prey's final line of defense operates. And that line is about being impossible to process, which has nothing to do with escaping. Too hard, too spiky, too poisonous, too big for the opening. Start with hard, because armor is the oldest answer in the book, and it forced the most obvious counter-engineering. A sea urchin is a sphere of calcium carbonate plates covered in movable spines, and inside it is a small amount of extremely nutritious tissue. To get at it, you have to get through a shell that's designed to fail messily rather than open cleanly. Snails and clams present the same accounting problem, with the added insult of a locking muscle. Evolution's response was to give predators a grinding mill in the back of the mouth. The Atlantic wolffish is the poster animal for this. It's a big, heavy-headed, unglamorous fish of the cold North Atlantic with a face that looks like a bad mood. At the front of the jaws, it has conical fangs for seizing and prying. Behind them, on the palate, and along the lower jaw sit rounded, crushing teeth. And further back, there's a bony plate in the throat that does the final grinding. A wolffish takes a whole sea urchin into its mouth and reduces it. And if you dissect the stomach of one, you'll find gravel-like fragments of shell and spine. That kind of work wrecks teeth. So the wolffish replaces them. Adults shed and regrow their crushing dentition on an annual cycle. And there's a stretch of the year, after spawning, when the new teeth haven't hardened and the animal's feeding is limited. It has scheduled downtime because of what it eats. Sharks arrived at the same solution independently. The horn shark's scientific family name means different teeth, which is exactly right. Pointed, grasping teeth at the front of the jaw, flat molar-like plates at the back. It hunts urchins and mollusks, crushes them in the back of the mouth, and in some populations, the teeth are stained purple from urchin pigment. Eagle rays and cownose rays went further, flattening the dentition into interlocking plates that work like a pavement, with new rows conveyor belting forward to replace what wears away. And on Atlantic and Gulf reefs, there's the sheep's head, a fish people photograph because its mouth is full of what look unnervingly like human teeth. Broad incisors at the front, molars behind. It eats barnacles and oysters, which is to say it eats things cemented to rock inside mineral houses. Line those four animals up. A cold water relative of the eelpouts, a shark, a ray, and a porgy. Four completely separate lineages, four independent arrivals at the same design, and the design is dictated entirely by the shell. The pufferfish belongs here, and it's the best animal in this whole section because it plays both roles at once. As a predator, a puffer has 4 teeth, just 4 fused into a hard beak, 2 above and 2 below. And that beak grows continuously because it grinds itself down on shellfish. Puffers eat crabs, mollusks, and urchins by cracking them. As prey, the puffer is where the ingestion problem gets vicious. The famous defense is inflation. A puffer's stomach is enormously elastic, and when threatened, the fish gulps water and pumps it in until the body becomes a rigid ball, several times its normal diameter. Porcupine fish add spines that lie flat until inflation raises them into a spiked sphere. Notice which stage that defense targets. Inflating does nothing to help a puffer escape. It cannot swim inflated. It has made itself slower, more conspicuous, and easier to catch. What it has done is make itself unswallowable. And that's a bet that the fight will be decided at the last threshold rather than the first ones. The bet pays. There are documented cases of large predatory fish and sharks found dead with an inflated puffer wedged in the throat or the jaws. The predator won detection, approach, the strike, and the grip. It got all the way to the last exam, failed it, and the failure was fatal. Then there's the chemistry. Many pufferfish carry tetrodotoxin, And it's worth being precise about this one because it gets sensationalized. Tetrodotoxin blocks the sodium channels that nerves use to fire, which means signals stop propagating, which means muscles stop responding, including the ones you breathe with. The fish doesn't manufacture it. The toxin is produced by bacteria and accumulates through the food chain, which is why puffers raised on clean feed in captivity can end up with little or none. For a predator, a puffer is a meal that can kill you after you've eaten it, and the animal doesn't have to survive the encounter for the defense to work. It only has to make eating puffers a losing long-term strategy for the predator's population. That's a defense operating on evolutionary time rather than on the individual. The puffer that gets eaten is still dead. Its relatives benefit. Now, hardness and poison are one branch of the last defense. The other branch is simpler, and in some ways harder to beat. You can just be too big to fit. Every predator that swallows prey whole is limited by gape, the maximum opening of its mouth. And gape limitation is one of the strongest organizing forces in marine food webs. It determines who can eat whom, and it means that growing is a defense. Get past the gape of the local predators, and an entire category of threat switches off. So prey animals evolved ways to be functionally bigger than they are. Triggerfish carry a first dorsal spine that locks upright. The mechanism is a smaller second spine that slides in behind it like a wedge, and it's where the name comes from. Release the second spine, and the first drops. A triggerfish wedges itself into a crevice, erects, and locks that spine, and becomes very difficult to pull out. The same locked spine also makes the fish awkward to swallow, adding height to a body that's already deep and flat. Surgeonfish carry a blade at the base of the tail, sharp enough to earn the name, that folds out. Lionfish spread venomous spines. Deep-bodied fish are simply tall in a way that has no hydrodynamic benefit and a very clear anti-swallowing one. Every one of those is aimed at the throat of a predator that has already caught the fish, and it's worth stopping on that, because it changes what these animals are telling you. A spine is a statement about what the losing scenario looked like often enough to matter. You don't evolve a locking dorsal spine unless a lot of your ancestors were briefly inside something and got spat back out. If gape is the limit, there are two ways to respond: get a bigger mouth or get a body that stops arguing about what fits. The deep sea did both, and it did them because of the same scarcity we talked about earlier. When encounters are rare, the worst possible trait is being fussy. A deep-sea predator that can only eat prey within a narrow size range is a deep-sea predator that will meet the wrong-sized animal, let it go, and possibly never meet another one. So down there, the ability to swallow became more important than the ability to chew, and evolution went at the skeleton with a crowbar. Several deep-sea fish have jaw suspension so loose that the whole feeding apparatus swings outward and forward, opening a gape far wider than the resting head. Some can rotate the skull backward on the spine, tilting the brain case to widen the opening. Ribs get reduced or lost, which sounds like a downgrade until you realize that ribs are the thing stopping a body cavity from expanding. Stomach walls become elastic sheets. The extreme version is a fish called the black swallower, and it's about 7 inches long. The black swallower's stomach hangs below the body like a bag and stretches to a degree that seems anatomically illegal. It swallows prey longer than its whole body, working the fish in head first, using its jaws in alternating bites, walking its mouth down the length of the meal. Once it's in, the stomach distends until the predator is a thin fish attached to an enormous transparent balloon with another fish visible inside it. There's a specimen from the Cayman Islands, collected in 2007, where a black swallower of a bit over 7 inches had swallowed a snake mackerel of around 34 inches, 4 times its own length and many times its mass. Here's how that specimen came to be collected. it was floating at the surface, dead. That's the failure mode. And it's how a large share of black swallower specimens in museum collections were obtained. The fish takes prey it can physically swallow but cannot digest fast enough. The meal begins to decompose inside the stomach. Decomposition produces gas. The gas inflates the swallower like a balloon and drags it upward through thousands of feet of water, into pressures and temperatures its body isn't built for. And it dies on the way and washes up on the surface, with its last meal still inside it. A predator killed by its own success. It won every exam and then couldn't process the prize. I think about that fish whenever someone describes evolution as producing perfect designs. What evolution produces is designs that work often enough. The black swallower's stomach is a bet. Take everything you meet because you might not meet anything else, and accept that sometimes the bet kills you. Over a population and over deep time, that bet apparently pays. For the individual floating dead at the surface, it clearly did not. The gulper eel is the other approach, and it's the one where the common story is wrong. Eurypharynx pelechinoides looks like a mouth with an eel attached. The jaws are enormous, far longer than the skull, hinged loosely and connected by an expandable pouch of skin, and the tail tapers away to a thin whip with a light organ at the end. Every documentary shot of this animal implies the obvious. A mouth that big must be for swallowing something huge. Stomach contents say otherwise. What's actually found inside gulper eels is mostly small stuff, crustaceans in particular, along with small fish and other bits. The best current reading is that the huge mouth works as a scoop or net, a way of engulfing a large volume of water and whatever happens to be suspended in it, rather than as a device for handling a single big animal, which is a more interesting answer once you weigh the scarcity again. In water where food is thin and scattered, one strategy is to become able to eat anything of any size that you bump into. Another is to become able to filter a large volume of nearly empty water and take whatever's in it. Both are answers to emptiness. They just aim at different parts of the problem, and that second strategy, sweeping a big volume and keeping the contents, scales up in a way the first one never can. It scales up to the largest animals that have ever existed. Before we get to the biggest mouths, there's one more version of the ingestion problem worth looking at, and it's the one where a predator decides that most of the prey animal isn't worth the trouble. Since 2017, white sharks have been washing up on beaches in the western Cape of South Africa with a very particular set of injuries: a tear near the pectoral fins, the body otherwise intact, and the liver gone. 2 male killer whales have been identified in connection with these events, known to researchers by their damaged dorsal fins and nicknamed accordingly, and Alison Towner and her colleagues have documented the pattern in a series of papers, including a later observation of a single killer whale killing a young white shark and extracting the liver in a matter of minutes. The choice of organ is the interesting part. A white shark's liver is enormous. In large sharks, it can account for a substantial fraction of total body mass, and it's loaded with oil. Sharks have no swim bladder, so the liver does double duty as a buoyancy organ and an energy store, which means it's the fattiest, most calorie-dense tissue in the animal by a wide margin. Muscle is protein. The liver is fuel, so a killer whale that opens a shark, takes the liver, and leaves the rest is doing the same thing you'd do with a whole roast chicken if you only had 30 seconds. Go for the part with the calories in it. Handling time is a real constraint. Chewing through a shark's muscle and cartilage costs effort for a poor return. The liver is a single soft mass of fat that can be removed in one action. That's an ingestion stage specialization, and it belongs in this section rather than the earlier ones, because the killing was never the difficult part for an animal like that. The optimization is entirely about what happens after, and the consequence is the part that makes this more than a gruesome anecdote. The white sharks left. Gansby was one of the most reliable places on Earth to see a white shark. After these predation events, sightings collapsed, and the studies tracking it described long-term flight responses, with tagged sharks leaving the area for extended periods after killer whales showed up. The population appears to have redistributed along the coast. Other species moved into the space that opened up, including 7-gill sharks that had previously been staying away. Look at what the arms race looked like there. The shark's entire arsenal, the size, the teeth, the speed, the sensory equipment we spent the first half of this video admiring, offered no answer at all. There was no counter-weapon available. The only response in the shark's repertoire that worked was to go somewhere else. And an entire local population did exactly that. And a whole ecosystem rearranged itself around the decision, which is a useful thing to keep in mind. Not every move in an arms race is anatomical. Sometimes the counter-adaptation is a change of address. Now the biggest mouths. Rorquals are the group of baleen whales that includes the blue whale, the fin whale, and the humpback. And they feed by doing something so violent and so expensive that biologists took a long time to appreciate what it costs. A rorqual lunge starts with acceleration. The whale drives toward a patch of krill or small fish, and then it opens its mouth to something close to a right angle. The lower jaw bones are not fused at the front the way ours are. They're joined by fibrous tissue that allows the two halves to rotate outward and spread apart. And the throat, from the chin back along the belly, is pleated. Dozens of long grooves in the skin that unfold like an accordion. Water pours in, and the throat balloons into a vast sac. The volume of water a rorqual engulfs in a single lunge can equal or exceed the whale's own body mass. A blue whale takes in more than its own weight in water and prey in one gulp. Then the mouth closes, and the throat contracts, forcing all of that water out through the baleen plates, which are keratin, the same material as your fingernails, fringed into a mat of coarse hair. The water goes. Everything solid stays. Now that maneuver is spectacular, and here's what people usually skip. It's brutally expensive. Opening a mouth that wide at speed turns the whale into a parachute. The drag is enormous. The whale decelerates hard, and it then has to accelerate the engulfed water along with itself. Estimates of the energetic cost of a single lunge put it among the most expensive individual movements performed by any animal, which sets up a hard economic condition. A lunge only pays if the mouthful is dense enough with food to cover the cost of the lunge. Sparse prey is a losing proposition. The whale is hunting for krill packed tightly enough to justify a maneuver that can cost more than it returns. There's a piece of anatomy that appears to serve that calculation. In 2012, Nicholas Pienson and colleagues described a sensory organ sitting in the fibrous joint at the front of the lower jaws in rorquals, full of nerve endings and connective tissue, positioned exactly where the jaw rotation and the throat expansion would be registered. Their interpretation is that it gives the whale feedback on the geometry of the lunge as it happens, coordinating a movement that has to be timed to a fraction of a second. An organ whose job is to tell a whale how its own mouth is doing, mid-gulp. And now put the pieces together, because this is where the whole video's argument arrives at its largest possible scale. Why is there krill packed densely enough to make that lunge worth doing? Because krill swarm. They aggregate into dense patches, sometimes thousands of individuals per cubic meter. And they do it for the same reasons the sardines did: dilution, confusion, the safety of being one of a very large number. Swarming is a defense. It works extremely well against the animals that eat krill one at a time, and most animals that eat krill do exactly that. But a defense that concentrates thousands of prey animals into a small volume is also, from a different point of view, a service. The lunge-feeding whale is only viable because its food huddles. The single largest feeding structure that has ever evolved on this planet, the expandable throat of a blue whale, exists as a direct consequence of the fact that very small animals learn to crowd together to stay alive. Their defense built that mouth. Let's run the whole thing back as one sequence, because the shape of it matters more than any individual animal. A predator has to detect prey that has spent millions of years learning to be undetectable, using senses built specifically to defeat whichever hiding method the local prey favors. Then it has to approach through a fluid that broadcasts its every movement to animals equipped with dedicated flow sensors and reflexes measured in milliseconds. Then it has to land a strike inside a window narrower than the prey's reaction time, using speed it probably can't generate with muscle alone. Then it has to hold on to a slippery, panicking animal in a medium that offers nothing to brace against. And then, having done all of that, it has to get the thing inside its body without being poisoned, punctured, choked, or split open. 5 thresholds, 5 different sets of physics, 5 separate ways to fail, and most predators fail most of the time. That's the statistic that surprises people, and it's consistent across the ocean. The success rates for individual hunting attempts in well-studied marine predators tend to sit well below half, sometimes far below, and the animals we think of as unstoppable are often the ones with the least impressive numbers because they're targeting the hardest prey. There's a reason the odds sit where they do, and it was named in 1979 by Richard Dawkins and John Krebs in a paper about evolutionary arms races. They called it the life dinner principle. It goes like this. A fox chasing a rabbit is running for its dinner. The rabbit is running for its life. Both animals are under selection to be better at running, but the stakes are wildly unequal. A fox that fails goes hungry and tries again tomorrow. A rabbit that fails has no tomorrow and leaves no descendants. That asymmetry tilts the whole race. Failure is more expensive for the prey, so selection presses harder on the defensive side, generation after generation, which means that on average, over deep time, defenses get refined more aggressively than attacks do. And that finally explains the thing this whole video has been circling. The reason ocean weaponry is so extreme, so specialized, so physically absurd is that it has to be. A predator is playing against an opponent whose every failure was fatal and therefore removed from the gene pool immediately. The prey side of this race has been edited with a harsher pen. To stay in business at all against an opponent like that, a predator can't afford a general-purpose solution. It has to find one narrow, exploitable weakness and build its entire body around exploiting it, which is exactly what we've been looking at all along. A seahorse that gave up swimming to own a snout shape, a frogfish that gave up mobility to own a mouth, a moray that rebuilt its throat because prey hid in holes, a cone snail that gave up on speed entirely and went after the fish's blood sugar. There are limits, of course, and it's worth being honest about them, because arms race language can make this sound like an escalation with no ceiling. It has plenty of ceilings. Weapons cost energy and tissue and development time, and every specialization closes doors. The frogfish can't chase, the seahorse can't fight, the mantis shrimp has to reload. Beyond a certain point, a better weapon costs more than the extra food it brings in. And selection stops pushing. There's also an ecological break. A predator that gets too good at eating one prey species destroys its own food supply. And predators that do that don't last. The arms race is held in a kind of tension, with both sides constrained by their own costs, which is why these relationships can persist for tens of millions of years without either side winning. Every relationship in this video is a standoff, a very old, very violent, very stable standoff. And then there's us, which I'll spend exactly one paragraph on because it belongs here and it doesn't need a speech. Human beings are the only predator that solved all 5 thresholds without paying for any of them anatomically. Sonar and satellites for detection, engines for approach, nets and lines for the strike and the grip, refrigeration and processing for ingestion. We got every capability in this video without the trade-offs that constrain every animal in it, which is why our effect on marine populations doesn't look like anything else in the fossil record. No moral lecture is intended there. It's a structural observation about what happens when one player in an arms race stops obeying the rules that hold the whole system in balance. Everything else out there is still playing by them. Right now, as you're listening to this, in every ocean on the planet, the same 5 exams are being administered on a scale nobody could count, and the overwhelming majority of the animals taking them are failing. So there's one last way to read everything in this video, and I've been building toward it the whole time. Treat each weapon as a measuring instrument. That sounds like a metaphor, and it's closer to a literal description of what evolution actually does. A weapon gets more extreme only as long as the extra cost keeps buying extra meals. And the thing that determines how much extreme is worth paying for is the quality of the defense on the other side. Which means the severity of any given adaptation is a reading. It tells you quantitatively how hard the problem was. So run the list again and read the numbers off. A shark's electrical sense is calibrated to about 5 billionths of a volt across a centimeter. That's a measurement of how completely a flatfish can disappear. The instrument had to be that good because the camouflage was that good. The dragonfish's private red searchlight is a measurement of how convincing counter-illumination had become. You don't invent an invisible color unless visible light stopped working. The seahorse's snout, that whole peculiar tube, is a measurement of how sensitive a copepod's antennae are to moving water. Every curve of it is shaped by the threshold at which a grain of rice-sized crustacean decides to leave. The mantis shrimp's club, with its crack-resistant layered architecture and its cavitating strike, is a measurement of snail shell. All that engineering is a readout of how thick, how tough, and how well-shaped the armor got. The moray's second set of jaws, launching forward out of the throat, is a measurement of the depth of a coral crevice. The prey chose a hiding place that broke the standard feeding system, and the throat is the size of the answer. The cone snail's venom, with its coordinated cabals and its weaponized insulin, is a measurement of the gap between a snail's top speed and a fish's. The bigger the gap, the more elaborate the chemistry has to be, and that chemistry is elaborate enough to have produced a modern painkiller. The sea star's hours of unbroken tension is a measurement of a muscle's catch muscle, an organ that can stay locked almost for free. Beat that with force, and you'd need a hammer. Beat it with time, and you need most of a day. The cookie-cutter shark's rotating bite is a measurement of how well being enormous protects you. The wolffish's grinding plates, replaced every year because they wear out, are a measurement of an urchin's shell. That annual downtime is the invoice. And the pleated, expandable throat of a blue whale, the largest feeding structure that has ever existed on this planet, is a measurement of how tightly krill press together when they're frightened. Every single one of those weapons is a portrait of something that was very good at staying alive. Before the last thought, one thing I'd actually like from you, and it's a real question rather than a formality. Out of those 5 thresholds, detection, approach, the strike, the grip, and swallowing, one of them is the one you'd least want to be standing on the wrong side of. Tell me which, and tell me why. Because the answers to that split people in a way I find fascinating, and the comments on this kind of question usually teach me something I didn't have when I wrote the script. If you've got a defense you think deserved more time here, put that down too. There were a dozen I had to cut. And if you'd like more of this sort of thing, the long, slow, mechanism-first kind, subscribing is the way to get it. A like helps, and honestly, so does telling me what you want the next one to be about. Now the last thought. We started this by calling these adaptations brutal, and the material earned the word. The strikes are fast enough to boil water. The teeth are shaped so that struggling makes things worse. The chemistry shuts down nervous systems in seconds. But brutality, in evolution, is never self-generated. Nothing gets to be that severe on its own. Severity is a response, and it only escalates as far as it's forced to. So the ocean's arsenal, laid out end to end, all those clubs and hooks and fangs and harpoons and second jaws and expandable stomachs and searchlights, is a record of what those hunters were up against. Read it backwards, and every weapon names its opponent. The hammer names the shell. The searchlight names the disguise. The venom names the speed it couldn't match. The enormous mouth names the crowd, which means the most brutal predatory adaptations in the sea are, in the end, a description of the animals that were being hunted, an inventory of how good the hunted got. The armor, the stillness, the alarms, the slime, the locking spines, the swarms, the ability to vanish in an open ocean with nowhere to hide. The predators wrote it all down, in their own bodies, every single time they had to try harder.